Hey, this is a short introduction to the chapter review. Part of it includes some exercises in solving for roots of equations or solutions to like quadratic equations using a calculator. And so I recorded this as an introduction to that segment. So worksheet 16 is a worksheet where we look at how to solve for roots of equations. So that requires just a little bit of math background. If you have a linear equation, say it's 2, let me get a pen out here, 2x minus 3 equals 0, for example, and you want to solve the root of the equation. The root is when the value of x, quote unquote, satisfies the equation. So what that means is the value of x makes the left and right hand sides of the equations true. Now, in a chemical problem, what we're going to be doing is we're going to be solving equations and looking for roots, which are actually concentrations of reactants or products, or related to concentrations of reactants and products. So take a look at this first expression. This is a second order expression. It'll have potentially two roots. Now, what is a root, right? If you're thinking about what it looks like when you graph an equation, not all equations have roots. But an equation looks something like that. That would be sort of a quadratic form. It's got that parabolic shape, can go either upwards or downwards, but the roots are where the y value crosses the x-axis. So it's the x-axis crossing point. Well, if you think about it like that, in a quadratic equation, you can have potentially two roots. They could have a positive and a negative, but sometimes you can have two positive roots. It just depends on what the arguments in the expression are. If we want to solve this equation to find its roots, what we end up doing is going like x squared over 0.1 minus 2x, that whole quantity squared, is equal to minus 155 equals 0. And then you're going to be looking for the conditions in which, in this case, an equilibrium constant satisfies this is the equilibrium constant over here, the way we do them in class, satisfies the conditions where the values of x minus 155 equals 0. Now, oftentimes in a chemical problem, we get two roots. And in chemistry, the root expresses a concentration. And so the thing is the roots can never be 0. So this term boundary conditions, well, I guess the roots could potentially be 0, but they aren't in these cases. But they can never be below 0. So because you can't have a negative concentration. So the boundary conditions are the values which give you valid roots for a particular type of problem. So in the chemical equilibrium problem, those values always have to be greater than 0. So we would call that, it turns out to be the left boundary condition is 0. And then there's also an upper bound, because it is possible that one of the roots could make this term negative. Now, when we're writing equilibrium constant expressions, both the value of x represents a concentration, but also these terms in brackets represent concentrations. So those can't be negative either. So if you're thinking about what the largest value of x can be, what you have to do is you have to say 0.1 minus 2x equals 0. That'll tell you when that particular expression crosses 0. And so now you can say 2x is equal to 0.1, and so x is equal to 0.05. That's known as the upper bound for this problem, because if x becomes bigger than that value, then this term becomes negative, which is also one of those conditions because we're dealing with chemical concentrations that can't be true. So our bounds, the left bound is 0, and the lower bound is 0, and the upper bound is 0.05. Now, how do you solve these expressions in your calculator? So what I did was I pulled up an emulator for a TI-84 calculator, but I'm also going to show you on Wolfram Alpha how to do it. Since this is an online version of the class, you have access to some of these tools that you wouldn't normally. Okay, so what I'm going to do next is I'll open up the emulator. Oh, and make note of the equation. It's x squared divided by 0.1 minus 2x squared is equal to 155. Okay, so now we'll go over the emulator and I'll show you how to enter that in. Okay, so to start with, you notice there's a math button here. So what I'm going to do is click on that. And then you can page down or page up, but it's actually at the very bottom. And it's usually here, solver. Now it might not be B, it depends on which calculator you have. So we're going to go ahead and click that. And I just hit enter to get there. And now what it does is it shows me the equation, and you'll notice it says E1 equals E2. So there's two ways you can do this, but I'm going to follow the traditional format where one side is actually 0 and the other side is the equation. So I'm going to say x squared, so I have to find my variable x, and then I have to square it. And I'm going to say divided by, and I need a parenthesis, because if you go back and you look at your equation, that's the way it's formatted. And you do have to be really careful with these equations that you use the parentheses correctly. Because if you don't include a parenthesis, then you're not going to necessarily be dividing, let's say, by the whole denominator. Oops, sorry, wrong one. So, 0.1 minus 2x squared. So I'm going to say 0.1 minus 2x squared, and that was the whole quantity squared. So I'll close the parenthesis and I'll square it, and then I'll hit enter. Oh, sorry, I was going to do the other way, huh? So let me go back up, and then I need to go to the right. I was going to do it the more traditional way of doing it. This is the way that's in all of the older TI calculators, minus 155. And then I can go down, and then over here I'd put 0. Now, because if you have this calculator, what you can actually do is put 155 in there, and then just make this expression x squared divided by 0.1 minus 2x. Now that we're there, we're going to hit enter. And you notice down here it's asking you to put the bounds in. And you can do that. Our bounds will be 0 and 0.05. Those are the lower and the upper bounds. So if you put those in there, then the calculator won't solve for other bounds. So I didn't get rid of the E99 because 0E99 is still 0. And then I'm going to put 0.05 here, and then I'll have to delete that 9, so I'll hit delete. And I'll go back up to here, and then what I need to do next is solve for the value. Now you notice it says here, press alpha solve. And you notice there's the alpha, that's the green key, and the solve is over here. So it's just alpha enter. So I'm going to go alpha enter. And it took as the left bound 0 as the starting point for x. And I generally recommend that you put that value in there so that it starts on one boundary and then moves towards another. So this is actually one of the roots of the equation. It's 0.048069. So for practical purposes in a problem like this, it's typically about 2 or 3 significant figures. So we would take that as 0.0481. So let me go over there and I'll write that down. So one of the roots is 0.0481, and these are equilibrium concentrations, so this would be a molarity. Now, it turns out if you wanted to find the other bound, okay, then what you have to do is you either have to look to the left of the lower bound that gave us this answer, or to the right of the upper bound. Sometimes it's a fairly simple matter of just putting a negative value in. So we're going to go ahead and clear this boundary condition, I think. Oh, actually, I keep trying to click on it with a mouse. I don't know what will happen is if I delete this. Will it fill it in? Oh, nope, it will not fill it in. So let me quit, and I'll go back in to math, and then we'll go back. I'm going to go from the bottom to solver, and I'm going to hit enter. Enter. It remembered everything I did. Oh yeah, and then it filled the bounds back in. So what I'm going to do with this number now is I'm going to put a negative value in. So I'm going to just say -5 just for fun, and let's see what happens. And this may or may not work. And now we're just going to solve it. It's kind of an annoying way to find the other bounds. No sign change, which means it got to a point where it couldn't. I'll explain it to you when we go back. Let's go back to it. I'll show it to you. So what it's doing when it does this calculation is it does the calculation twice and then tries to detect a change in sign in this equation. So what it's actually doing is plugging in values of x and then looking to see if it can get a value where this expression minus this one changes sign. If it does that, then it's found a root of an equation. Apparently, I just broke it by adding a bad value to it. Let's try 1, and let's try that. Again, this is not a guarantee to find an answer, so I figured I'd just show you how this goes in real life. And then I'll show you the way I'd expect you to do it in a second. Nope, not finding it. So I'm going to go to the problem again, and what I'm going to do is clear this, and I'm going to put a value that's bigger than 1. And it may be a divide by 0 kind of error. I'm not sure. I'll do it one more time. Yeah, and there's the other root. So it turns out the other root was above the upper bound. Remember, the upper bound that we had before was 0.05. So this one's greater than 0.05. So it's 0.0521. So I'm going to write the other bound, other root as 0.0521. And this is, again, molarity units. Now, the reason, again, why this root of this equation is not valid is because if I take 0.1 and I subtract 2 times 0.0521, like this value is negative. This is clearly going to be bigger than 0.1. It's like 0.0041 negative. So that being said, it doesn't qualify as a root for this problem because in chemical problems we want the concentrations to be all positive values. That is, positive roots, but the expressions themselves also have to be positive. So that turns out to be a nice thing because it's usually the root that these calculators will solve for. So now what I'm going to do is I'm going to show you another option, and that's in Wolfram Alpha. Okay, so I've already entered it once, so that's why you can see down here, but I'm just going to show you how you enter it. This is Wolfram Alpha, and I've talked about this site before, so some of you probably are using it. So what I'm going to do is I'm going to go ahead and plug in x squared divided by open parenthesis 0.1 minus 2x squared equals 155. Now, while this is thinking, it doesn't take long. While you can't use this on your final, what you'll be learning in this worksheet is that there's a way to approximate and get answers. It works much of the time in many of the problems that we do, not all the problems. But the ones that you end up having to do on your final, for example, all only require the approximation method. So as far as tools go, this is super helpful to get you through the math and help you understand the concepts of the chemical problem. But as far as in the future, like for you're taking your final and going on, um, the concepts are really what's important, and the calculations can all be done using an approximation method that I'll show you at the end of the worksheet. So that being said, 0.0481 rounding to 3 sig figs and 0.0521 are the same answers that we got on our worksheet over here. Now, having said that, all right, those are the answers. You still have to understand that it's this root is the correct root of the equation for us. It's always the smallest positive root of the equation. So this next problem, this part B, I found to be really useful in helping students to understand the relationship between ice tables, equilibrium constant expressions, and the sort of calculation setup that we do in these problems. And it helps them recognize when they make mistakes in setting up ice table problems. So let's say you had a reaction. Let's just for now say it's A plus B makes C plus D, and then I'm going to make this 2D like that, just to add some variation to it. And what does the equilibrium constant expression look like, right? So the equilibrium constant expression would just be K is equal to, and then products, C times D squared over reactants, A times B. And if you look at a nice table that you might set up, let's just say you start with reactants, right? Let's say they're 1 molar or something like that. So we're going to have A plus B makes C plus 2D. And so this will be, let's say 1 and 1 and 0 and 0, kind of like a lot of problems start out, no product, all reactant. And then you know this will be minus X, and this will be minus X. And this will be just X, and this will be 2X. So plus, right? So when you set this up, then what's going to end up happening on the bottom line is this is the initial, this is my change, this is my equilibrium. My equilibrium line will look like this: 1 minus X, 1 minus X, and then X and 2X. Now, notice, like if I were to write this into here, right, my products would be X times 2X squared, like that. And this 2 that's here and this 2 that's here in the order both come from the stoichiometric coefficient. And then when I'm dividing, it's going to be 1 minus X squared, something like that. And you'll notice that you have a square here, a 2 here, but you don't have it here. And that's the indication that there are actually 2 different reactants that led to that expression. So you know you have 2 reactants in this one. You know you have 2 products. It's just one of them has a coefficient of 2 on it. Okay, so this should help you. This sort of exercise should help you sort of understand what equilibrium constant expressions should look like, and it should help you avoid some real common errors. So let's go ahead and do this first one, right? And this is my expression. I'm just going to rewrite it here. It's X squared over 0.1 minus 2X squared. And again, this is products over reactants. Now, you notice I have an X squared and not a 2X squared at the top. So what that tells me is my products look something like this. And in terms of A, B's, and C's, I'm going to just say it's B plus C for now. I kind of know what the problem looks like already. And then what did those come from? Because that's the product side. And because there wasn't a 2 with the X, I knew it had to be 2 individual products. So those are B and C. Then my reactant that gave me this has to be 2A, like that. And the reason I say it has to be 2A is because there's both a 2 here and a 2 here. And that 2 those 2's come from the stoichiometric coefficient. And it started with a concentration of 0.1 molar. And so now you can fill in the ice table. This is initial conditions are 0.1, and this is 0 and 0, because if they weren't 0, they would have had numbers associated with them up here, right? And then you can fill out the rest of the ice table from there, following this procedure that kind of showed over here. One other thing to cover, and I don't know if I already said this. I started saying it earlier, and then I think I might have deleted it. But on your final, you don't get to use a solver, and you don't get to use Wolfram Alpha. So, like, how is this helping you, right? Turns out all the problems that you'll get that require a calculation like this can be done by a method of approximation. That's one thing. And the other thing is really what's important is that you understand the concepts of what's going on. Because the final in these sections is more about the concepts than it is about the actual calculations. There might be one or two where you have to solve for a root of equation out of 70 problems, but really not much in terms of percentage of the test. And when you do have to solve for it, you can almost always approximate it. So let me show you what I mean by the method of approximation. The method of approximation only works, and your book has a big section on this. I'm sure it's there somewhere. But the bottom line is this. If the concentration of the reactant is greater than 100 times the K value, in other words, the K is really small, right? Then you can use the method of approximation. Okay, so this is the concentration of reactant. Now, it's not always true, but it is almost always true for the kinds of problems that we do. So K has to be more than 100 times smaller than C. When you do that, and now take a look at this problem. We're starting off with 0.12 molar. And then these are 0 and 0, and then this is our equilibrium constant. So I'm going to let you set up the ice table for the expression, but your expression will look like this. And you can check, but this one it's already true, but you can check if you take this number and divide it into this number and it's bigger than 100, then this statement is true. That's usually the way people do it. They take their concentration and they divide it by their equilibrium constant and they look for a number greater than 100. So, that being said, what does it mean to answer by approximation? Well, one, you're going to use your solver. That's what you're supposed to do here, use your solver. But here now we're going to do it by approximation. And by approximation, it simply means if the equilibrium constant is small, then the amount of material that dissociates of the original material will be small relative to this number, right? Because X represents the amount of material, in this case, which ionizes. And if K is really small, then generally speaking, X will be small relative to the concentration. And then what we can write is this, X squared over 0.12 is equal to 2.1 times 10 to the minus 4. And now you can solve that for X just by rearrangement and then taking the square root. Now, you're going to do the same thing in problem 5. And you're going to use the method of approximation and show that it doesn't work in this case. And notice the concentration of the formic acid. This is the formic acid up here, right? It's 0.00012, and it's of the same order of magnitude, 1.2 times 10 to the minus 4th versus 2.1 times 10 to the minus 4th. The approximation shouldn't hold under these conditions. So what you're going to do is you're going to set it up, and you're going to solve it using a solver, and then you're going to use the approximation method, and then you're going to calculate the percent error in the approximation method answer. And then you could state clearly like why the approximation failed in 5B.